Hi, William.
Hello, how's it going? Can you hear me?
Wait a minute.
We've seen.
Wait. So,
Oh,
hello everyone.
is this?
Today we have William Dudarov from University of Washington. He is a BSc student there, and he plans to speak on a paper of Henry Darmon with the same title as Darmon's 14th lecture on Fermat's theorem. Okay.
Thank you.
Over to you, William.
Thank you very much. So we've seen Angelos's talk this past Thursday on Darmon's program, which was fantastic and full of detail. And in this discussion talk, I just wanted to try to cover this survey, the survey article that Darmon wrote. Not all of it, but specifically towards the beginning, where he gives a alternative proof of a result of Andrew Granville, that actually predates Wiles's proof of Fermat's last theorem on the generalized Fermat equation. So, as we know from Angelos's talk, we are interested in the generalized Fermat equation. I'll just abbreviate that to FE. And we are specifically interested in non-trivial solutions. So x, y, z not equal to 0. We're interested in primitive solutions, primitive integer solutions. So GCD, greatest common denominator of x, y, and z is equal to 1. And this is just because non-primitive solutions are easy to construct from the primitive ones. And so the main conjecture that I wanted to state, kind of the whole goal of the of Darmon's program is the following. When 1 over p plus 1 over q plus 1 over r is less than 1, the generalized Fermat equation has no non-trivial primitive solutions. Except for the 10 following. 1 to the p equals 2 to the 3 equals 3 squared. 2 to the 5 plus 7 squared equals 3 to the 4. Seven to the 3 plus 13 squared equals 2 to the 9. 2 to the 7 plus 17 to the 3 is 71 squared.
You can skip maybe.
Yeah.
This is there.
So there's 10 of these. And that's a you know, an interesting conjecture. So the generalized thermal equation may seem kind of exorbitantly difficult given how the regular, you know, Fermat's last theorem was to prove. But as we've seen in Angelos's talk, some cases are doable with modern methods. And it's important to note that there were big results on the generalized Fermat equation, even from before Wiles's Fermat's last theorem proof. In particular, I wanted to highlight in this talk specifically a theorem of Andrew Granville from 1993. So theorem is suppose P, Q, R are fixed. And satisfy. I'm taking all these theorem statements directly from the paper. 1 over P plus 1 over Q plus 1 over R is less than 1. Then the equation x to the P plus y to the Q plus c to the R has finitely many primitive solutions, integer solutions. So the main point of this talk is to try to prove this, and it's a little hard. There are a couple of propositions which we will not prove, but one of their proofs is listed is given a sketch in Darmon survey. But okay, yeah. So we can get started. And since, you know, we're skipping a couple of like dilemmas needed for this proof, I guess this is more of a proof sketch, but kind of a long one. So the proof of this theorem relies on the properties of the Hecke triangle group, gamma PQR. Generated by, gamma 0, gamma 1, gamma infinity, satisfying gamma 0 to the P equals gamma 1 to the Q equals gamma infinity to the R equals gamma 0, gamma 1, gamma infinity equals 1. And it's important to note here that we can actually say, we can actually make sense of like P or Q or R, or all three of them equal infinity. And in this case, we'd say if P equals infinity, then x infinity is 1 if x is 1, or infinity if it's not. And same thing for y infinity, z infinity. And so if one of P, Q, or R is equal to infinity, then the corresponding gamma J is of infinite order. So what is this hecatriangle group? Let's recall that it is finite if and only if 1 over P plus 1 over Q plus 1 over R is greater than 1, and it's infinite and non-abelian, necessarily non-abelian if 1 over P plus 1 over Q plus 1 over R is less than 1. So why is this? So let tau 0 or t, t1, t infinity denote the reflections about the sides of a triangle, I guess triangle PQR, with opposite angles pi over P, pi over Q, pi over R. I guess this is not exactly necessary. But the rotation is sigma 0 equals T1 T infinity, sigma 1 T infinity T0, sigma infinity T0 T1. Satisfy the exact same relation as the gamma J's that we saw above do. So namely, sigma 0 to the P equals sigma 1 to the Q equals sigma infinity to the R is equal to sigma 0, sigma 1, sigma infinity equals 1. So Darmon in the article says, so setting sigma j equal to gamma j, we realize gamma PQR as a group of isometries on the underlying plane geometry. With two copies of the triangle as a fundamental region. And so if 1 over P plus 1 over Q plus 1 over R is greater than 1, triangle PQR can be drawn on the sphere. It's equal to 1 on the Euclidean plane. It's less than 1 then on the Poincare upper half plane. So the set of complex numbers with positive imaginary part. So in this last case, gamma PQR is a discrete group of isometries on H with the hyperbolic metric. Thus, we can think of gamma PQR as being embedded in PSL2R. And this, Darmon says, means that gamma, we can say that gamma PQR has a lot of quotients. And we'll mention this towards the end of this talk again. So we can note that gamma PQR is a quotient gamma infinity, infinity, infinity. And this is the fundamental group of P1 minus 0, 1, and infinity. Thus, if we have any surjective homomorphism of groups phi to G composed with the natural surjective homomorphism we get a surjection from the fundamental group of P1 minus these 3 points to G, and this corresponds to a ramified Galois covering.
What is G?
G is just another group from which you can
Okay, so any group which is having this map.
yes. Oh yeah, you can think of like G is a quotient of gamma PQR. So this corresponds to a ramified Galois covering of topological spaces with Galois group G.
I see. For everything, it would be Galois.
Sorry?
For every kind of group, it would be Galois.
I believe so. Yes. Yeah.
Okay.
Yeah, so this corresponds to ramified Galois covering of topological spaces with, well, we can just say that G is a quotient of gamma PQR. of topological spaces with Galois group G. And through Serre's terminology, in his topics in Galois 3, we say that the covering is of signature PQR. So if you were wondering where that terminology came from in Angelos's talk. So through pi, X inherits the structure of a compact Riemann surface and by Riemann's existence theorem, X arises from an algebraic curve over C, but we can also define it over a finitely generated extension of Q, or we can just say that we define it over a number field K. So pi is a rational function defined over K.
Can you repeat this last thing?
Yes. So we have pi from a covering X to P1. We say the covering is of a signature PQR. Through P, X inherits the structure of a compact Riemann surface. By Riemann's existence theorem, X arises from a curve defined on C, or we can say a number, we can define it on number field K. And so pi can be thought of as a rational function over K.
Is it easy to find any number field given this much data for a particular triple?
I believe so. Yeah, I don't think that's a huge problem or a problem at all.
Okay, so now we'll set up over the number field K.
Sorry?
Now whole setup is on number field K instead of C as a Riemann surface.
Yes.
Okay.
Yeah. Yeah. So let pi PQR be the set of primitive integer solutions. And let sigma QR the set of AP over CR, sorry, such that ABC is is a primitive solution. And this is a subset of P1Q. This can be embedded in P1Q. So to prove theorem 2, to prove the theorem, the Granville theorem, we actually just need to show that sigma PQR is finite. And so we give one last definition for T and P1Q. We define LT as the field generated over K by the coordinates of pi inverse T. So we have the following proposition, which we will not prove. But there is a proof sketch in Darmon's survey. There exists a finite set S of primes of K such that LT is unramified outside of S. Yes. For all T. This is an extension of the Chevalier-Vey theorem for ramified coverings. And to control the possibilities of what LT can have, we actually have the following proposition. Sorry?
This is extension of whose theorem?
Of Chevalier-Vey for ramified coverings.
I see.
So yeah, this proposition tells us that as t varies, the number of fields LT is finite. And in particular, the compositum is a finite extension of K. Finitely, yeah. Finite extension.
P is from P1Q, right?
Sorry?
P is from P1Q or this set?
P is from T or
T.
yeah, T is from
Okay.
from this set.
From theorem in his paper, yeah.
But we can say that we can note that this is contained in pi x L. So the theorem is a question about the finiteness of algebraic points on the curve x over a number field, over a single number field L. I'll give one more proposition. Curve x has genus strictly greater than 1. And this actually just follows by Riemann-Hurwitz. And the last thing that we need is, now that we have everything built up here, by Fourteenth's theorem, XL is finite since X is a curve of genus strictly greater than 1, and L is a number field. And so the theorem is proved after all this work building up to it. And so the approach that we saw for proving this theorem kind of gives us a general principle which tells us there is a dictionary between strategies for studying the generalized Riemann sorry, the generalized Fermat equation. And finite quotients. P of gamma PQR of this Hecke triangle group. So if we have a quotient, we studied the corresponding G covering. Determine a finite extension L of K satisfying and we try to understand XL as much as we can, as precisely as possible. And that's our general strategy. Thank you very much for being here, and I want to thank the organizers of this program at ICER Pune and Bhaskaracharya Pratishthan.
So this pi XL is some subset of P1L.
Sorry?
Pi XL,
Mhm.
some subset of P1L, right?
Yes.
Pi is the mapping between X and P1 minus 3 point. So P1 or 1 minus 3 point over L, right?
Sorry?
But what is Darmon's theorem here?
He proved that key. Huh? He proved about that.
Yes.
That finite set. So it only guarantees the finiteness, but I think
Yes.
eliminating other possibilities, one has more finer study of this object XL, right?
Yes. Yeah, and that's, kind of and the rest of the survey kind of goes into that more, and the challenges that come with that.
So this Riemann existence theorems guarantee the number of field, okay?
The Riemann existence theorem, yeah, I mean, yeah, it tells us that the compact Riemann surface arises from an algebraic curve defined over C, and then we can just specialize to we can define it over a number field.
But I think it is quite non-trivial, and because of Bailey, you find the number field, or maybe.
Right.
Okay, thanks.
Thank you very much once
So,
again.
Yeah, we will end the meeting and I will let you know some details more. Thanks.
Thank you.
Have a nice day.
You too.